Okay, we'll start today's class. Week 4 of Design of Steel Structures taught by Professor Damodar Maiti. I am Trisha Chakraborty, one of the course teaching assistants of this course. I am a PhD student at the Indian Institute of Science, Bangalore. I'm going to start with a brief recap of the topic. Uh, the As we have spoken before, there are two broad branches of structural engineering: analysis and design. Analysis is the forward problem. Here we are given the structural dimensions, the boundary conditions, and the applied loads, and we have to find the response induced in the structure or in the structural elements individually, the forces, stresses, deflections, strains, etc. And design is the reverse of the inverse problem. I'm really sorry about that. Okay, and design is the inverse problem. The loads to be withstood by the structure will be given, and there will be certain criteria on the maximum deflection. So there will be a limit placed on the permissible force and the permissible deflection, and we have to find the optimum size of the structural elements. And design is what this course is focused on. The major courses of analysis we study in second year, structural analysis, and on design we have two courses in undergraduate, usually the design of RC structures and the design of steel structures. Now, steel versus concrete, because so far we have already looked at in your third year, you probably have already studied design of concrete structures. Concrete is the most versatile material for construction, so why would we use steel? Steel is a much stronger material than conventional concrete. It has a high strength to weight ratio. That means steel structures are lighter if they have to provide the same strength, and steel is ductile compared to concrete. It gives more warning before failure than concrete. So that is a very important uh, feature to have, especially in earthquake prone zones where warning could make the difference between saving the number of lives you can save. And steel is, however, much costlier than concrete. So most buildings we see around us, residential buildings, institutional buildings, are made of concrete, and steel we generally use to make bridges or factory sheds and or towers. Especially towers cannot be made by concrete because extreme strength is needed in the columns that are very tall in height and all. Why do we need design? The components individually and the entire structure should withstand the load throughout its lifespan, satisfying the serviceability criteria. The serviceability criteria, as I keep saying, has to do with the permissible deflection. That may seem unimportant compared to collapse criteria, but it is still a very important criteria. And the lifespan of a structure has to be defined before it is designed. It could be 50, 60 years, 100 years, 150 years. And to properly design a structure, we have to ensure that it is economical to construct without compromising safety. This is the most crucial part. We have to strike a balance between safety and economy. So we need cost effective design, and for that we have to have a good knowledge about the design procedure and all the ways we can utilize the material properties or the material behavior. The mechanical properties of steel that we take, irrespective of the grade of steel, uh, there are some properties that we take, that the Indian Standard Code 800 says to take these fixed values: the density, modulus of elasticity, Poisson's ratio, modulus of rigidity, and the coefficient of thermal expansion. And these are what defines the grade of steel, the yield stress Fy and the ultimate stress Fu that we get from the stress strain curve. And these are the rolled sections that, unlike concrete, as we have seen, that unlike concrete we use existing steel sections of specified dimensions in steel, and these are mostly hollow sections. These are not solid rectangles or squares like concrete. So the is handbook number 1 tabulates the weight per unit length geometric dimensions. Other dimensions like moment of inertia for these steel sections. This is a joist, this is a channel, this is an angle, this is a T section. These are some hollow sections, and these are rarely used. The bars, which are solid sections, and they have much smaller dimension than concrete solid sections, flats and plates. And there are some thing called stripes. I think flats, plates, and stripes are distinguished by the length to width ratio. But and these data will always be provided to you in a question. You do not have to remember any of these dimensions and properties. You just have to have a basic idea about what this is: the flange, the horizontal part is the flange, the vertical part is the web, and you have to know what is called by the thickness of web, what is the width of flange. Width of flange is this longer dimension, and the thickness of flange is this smaller dimension, this TF that is mentioned. Similarly, the depth of the web is small d, and the thickness of web TW is this small dimension. These terms you have to be familiar with, but apart from that, mostly you don't have to remember almost anything in this course. Everything will provide it to you. This is the stress strain curve that, or the elasticity curve, that is obtained by performing a tensile strength on a cylindrical specimen. This is how it looks like. A is the limit of proportionality. B is the elastic limit. So up to the limit of proportionality, the curve is a linear one. So stress is proportional to strain, and the slope, as we know, is the Young's modulus, or E. And then up to B, this AB part is non-linear. But why is it the limit of elasticity? Is why is the limit of elasticity? Because after up to B, if you load and then unload the, if you remove the load completely, the deflection will also go back to zero. So there will be no permanent deformation. But beyond C, that property does not hold anymore. So and D are the upper yield points and the lower yield point. But after which, beyond B, if you load and then completely remove the structure, completely remove the load, there will be a residual strain or a permanent set. And beyond D, the structure starts to flow, so it is called partially plastic. It is not elastic anymore. And yield stress, this corresponding to C and D, which are very closely spaced. The stress corresponding to these points is the Fy, or the yield stress. That for Fe410, that is a common grade of steel, it is 250 MPa megapascal. And after D, it starts to flow. So it we'll see that the stress, see, the strain is the cause and the stress developed is the response. Okay, in a structure, though we talk like stress versus strain. So strain is on the x-axis, that means strain is what we are applying, and stress is developed in the structure to resist the strain. So here you will see that the resistance provided is very less, even as the strain keeps on increasing. So it has attained plastic behavior. And E is the ultimate or maximum tensile strength, and F is the fracture point. E is corresponding to the Fu that we say here. This point, if then in Fe 410 is that this Fu, and Fy is 250 MPa. Modes of failure that we have seen in steel structures, there are several more modes of failure than in concrete ones. In concrete, the major ones were bending and shear. So here there are bending, local buckling, shear buckling, web crushing and buckling, lateral torsional buckling, and this is deflection. Deflection is the serviceability based criteria, and these are all collapse based criteria. So these all have to do with the structure failing, and deflection is these all have to do with the stress developed in the structure, as you can understand, and deflection has to do with the strain. So you can keep that as separate categories. But all of these have to be taken care of when we are designing. And why does this term buckling appear so many times? Because buckling occurs in sections that are slender. Slender means one dimension is much greater compared to the other dimensions. So in these in these steel sections, these this is how it can buckle. See, this part, this length is much larger than its width, and then width and thickness. So if it buckles, it will bend like this. That is not bending. I'm just saying to make you visualize that it will buckle something like this. It will attain a C kind of shape. These but in concrete buckling is not that important, because the sections are very thick. So like they're solid sections, so they don't buckle. And then design philosophies, the working stress method and the limit state method. The working stress method is an old dated one that used to be used earlier, but now we work almost entirely with the limit state method. Now we completely the code is entirely based on the limit state method. The basic philosophy here is that design action must be less than equal to the design strength. The design action is the action that we are designing it against, the load that we want it to resist, multiplied by a factor of safety, so that we design it against a higher load than we expect to come. And the design strength is got by the strength of the section divided by some value like 1.1, 1.25, so that we don't utilize the complete strength we would expect, the lesser strength than the complete capacity to be developed in the section. So the both these partial safety factors lead to safer design. The higher the partial safety factors are, safer the design would be. But again, it would start becoming uneconomical. So we have to strike a balance between the two. Now, connections. Connections are very important in steel structures because in steel structure, the sections, the beams, the columns that are made of sections are got ready-made from the factory, and they have to be connected. They are not cast as a whole like in concrete structures. So, connections is the first topic and one of the most important in this course. Last week, in week 3, we looked at bolted connections. So, this week we are going to look at welded connections. Connections are integral parts of any steel structures that have a major role in overall integrity. Standard parts are properly connected to create the steel structure. So these standard parts are the sections, and the structure is the overall structure that has to where the sections have to be connected at the joints. Connection make up a large amount of the cost of structural steel. So connection design should be given top priority for both safety and structural economy. Bolts and welds. Last time we discussed about bolts. So bolt is basically an external metal part which comes with a nut and a washer. Washer is not that important, maybe not, you can avoid it, but the nut and bolt is how it is connected. The bolt has a head like this and a shaft, and we drill holes in the plates, or in the, not the plates, the steel sections that have to be connected. We have to drill holes where the diameter of the hole is just a little larger than the diameter of the shaft. Then we insert it, and then we, and here is a nut. So we screw the nut in one sense, and we tighten the bolt. So tightening it, the more we have to tighten the bolt properly for the strength to be developed. And last class we saw that why, how the bolt, how the strength of the bolt is generated. There are two ways. One is that a tensile force, a compressive force is developed in the bolt, and it creates a compressive force between the two plates. We are calling it plates, but it could also be the web or flange of a joint or a joist or a channel. Okay, so between these two sections, compressive if a compressive force develops, a normal reaction develops, right? And we know that friction is mu into n, where mu is the static frictional coefficient, and n is a normal reaction between the two surfaces. So the bolt creates a compression, it creates a normal reaction, and multiplying it with mu, we get a force, and then that force develops in the lateral direction. So if a load tries to pull them apart or push them together, the friction will come into play. And then if there is some kind of displacement, if there is some kind of slip, then the friction stops acting. Though technically there is also a concept called dynamic friction. Dynamic friction does exist even between two surfaces that have relative movement, but during design, since we simplify and we want to work in the safer way, as soon as slip starts between the two surfaces, we do not consider the friction anymore, and we consider that the shearing and bearing of this bolt material is what is holding the structure together. So bolts develop their strength by three means. First is friction, then when the friction fails, it takes shearing and bearing, and if the bolt material is sheared through, like cleaved through, then the two plates will be wrenched apart and the structure and the connection fails. And if the connection fails, the structure may also eventually fail. Generally, the connection is the first thing that fails in a steel structure. So connection design is so important. And weld is different. Weld, the concept of weld is completely different from bolt. In weld, we do not have to drill a hole or anything. Here, this triangular part is the weld, and what is done generally, so this is made, these two are made of steel, right? These two plates or sections, whatever, we put we put a metal here, and we melt the metal and then allow it to cool down again, so it forms an integral sort of structure. So once the weld is made, you won't be able to distinguish between, you won't be able to see it separately. Like you can see the weld surface, but the bolt is a distinct element. But once the weld is made, it is part of the metal surface, and you cannot destroy it, you cannot pull it apart like the bolt. So these this is how welded connection is done. Welding is the procedure of joining two metal portions in the molten state with or without pressure. Electric arc welding is commonly used. You must have seen this in construction areas around you. They have the electric, the sparky electric thing, and someone wears the one doing the welding wears a protective guard in front of his on his eyes, because it is, you should not look at it with your naked eye. The part of the metal to be welded is melted by using electric arc or oxyacetylene flame along with a weld rod. You may also have done this experiment in first year. Generally, in colleges, we have a foundry lab where they make us do these things. I mean, it really helps if you have actually seen this closely to visualize what is actually happening. And then the arc heat will melt both the metal part and the rod at the same time. Okay, this I mean, when the melting is occurring, it's not just this extra metal that is melting. This part of the plate is also melting a bit, then so that when they cool down, they cool together and it becomes a solid structure, an integrated substructure. Fusion happens as welding rod material flows across the arc. Welding rod use may be shielded or unshielded. In the shielded type, this is just a general knowledge bit. It won't most probably be asked. The electrode will be coated with mineral compounds, flux producing a gaseous shield, which helps to avoid oxygen and thus stabilizing the arc. Advantages of welded connections: the joint efficiency is 100%. Why? What is meant by joint efficiency? See, in bolts, the whether or not when we are using a bolt with of a certain diameter, and then we do our calculations based on that diameter, that grade of steel of that bolt. However, in the site when it is actually been constructed, if the tightening is not done properly, the entire strength may not be generated at all. So the joint efficiency is like what we expect, it's a ratio of the developed strength by what we expect by in our hand calculations. So the joint efficiency in bolt is most often less than 100% because the tightening is not perfect. But in welds, there is no chance of that happening. Fabrication is in difficult structure is easy. uh, the welding process is much faster, and this is probably a little questionable. I don't know if pure silence prevails or not. The welding process is much faster, welding process is much economical as well, and this method always provides rigid joint, so there is no relative movement. In bolts, if the bolt hole is drilled a little too wider than the diameter of the bolt shaft, there may be some kind of relative movement between the two plates that we are bolting together. So it may not be completely rigid. There can be some kind of relative movement, but for weld, that doesn't happen. The method always provides rigid joints and minimum self weight for structure. See, when we are adding bolts, nuts, and washers, they have a lot more self weight than weld. Weld is just a bit of metal, but bolts are solid, proper structures, right? So the weight added by weld is less than the weight added by the bolts, and of course we prefer lesser weight of the structure, because self weight of the structure is also something that we design the structure for. We don't just design it for the external loads, we also design for the dead load or its own self weight. Design for disadvantages. Yes. Shikha, you ask
Hello,
something?
ma'am.
Yes, yes.
Yes, I have a doubt in bolts. Can I ask about the previous one?
Yes, can you ask after the class? Okay, okay, ask now.
Yes, I mean, particularly you have explained about the black bolts and the friction grip bolts,
Hmm.
and the formula is related to that. How friction grip bolts have the advantage of friction, and you are using the mu formula. That is all good, but how exactly? Because that seems to be friction between the plates. The bolt is
Yes,
not actually doing anything with respect to the friction. I feel even if with the black bolts, if it tight little more enough, maybe the
yes.
same kind of tightness can also be observed even with the black bolt. So how exactly friction grip bolts are providing the friction strength?
Okay, one second. I got what you mean. It's a good question actually. I'll have to think about it a little, because, like you're saying, that the strength of the bolt doesn't actually matter in the friction, because the friction is developed between the two plates. I'll
Yes,
search a little about it and let you know later, next class maybe.
sure, ma'am. Yeah, and also one more question I do have.
Yes.
Yes, and but when talking about particularly bearing type.
Yes.
Uh, okay. While calculating bearing strength of the bolt, we have formula kb into thickness of the plate,
Yes.
fy value of plate, and all. We are considering the properties of plate, and we are assigning it as strength of bearing strength of bolt. How is that
Yes.
justified?
See, actually, we don't use the we have to use the weaker. We have to use the strength of the weaker material, the plate or the bolt. If the bolt,
Hmm.
because it's about, even if it's the plate that is shearing, the ultimately the connection will fail. So it doesn't matter
Definitely.
to me whether the bolt fails in shear or the plate fails in shear. I want neither to fail in shear. So what we do is, in the formula we apply, we put the strength that is lesser between the plate and the bolt. Now you'll see that the grades of steel that is used in the plate and bolt, the bolts always have greater strength than the plates. That is,
But we use definitely the ultimate strength of the plate. The formula is like constructed for the to use the strength of the plate only. We don't have option like which is lower or lesser to use strength of the both the plate.
okay, 1 second, I'll open
Yes,
the code.
sure.
This is in shear capacity, right?
Yes, ma'am, that is shear capacity. And we bearing looks like KB into something, and KB is like 4. Ah, yes, this is the one. Little lower. Huh. Yes. Okay.
This one.
Yes, ma'am, yes. So the FU represented is
Ultimate
of the plate.
ultimate tensile strength of the plate. Okay, 1 second.
Hmm.
Design strength. See, this factor actually corrects it. See, this KB factor, if the FU is the smaller, right? So if the
Huh.
FUB is by chance lesser than FU, see what I am telling is, we expect that FU, that is the tensile strength of plate, is going to be always going to be lesser than FUB. So if that is the case, then this factor will be greater than 1,
Huh.
right? Then KB is the smaller of this, and 1. So this factor will not come into play when the FUB is greater than FU, which is what I'm saying happens most of the time. But if the FUB, that is the tensile strength of bolt, is lesser than tensile strength of plate, then this factor will be less than 1, and this factor will maybe incorporated here. I think these are two still more critical cases, but
Huh.
these two, I
Yes, ma'am.
think these two
Mhm.
also have to do with, like, they will be adjusted in some way, but this factor then also comes into play. I'm not sure this will be the factor that actually goes into the calculation.
Mostly in problems if you see in like in textbooks and all, mostly will be criteria of edge by 3D note and pitch by 3D note minus 2.5.
Yeah,
We
generally
rarely get the chance.
in the
Yes,
calculations that you have done, KB was coming out to be which value of these four? This is irrelevant.
first two.
The first two, right?
Yes, ma'am. First two are usually relevant.
So I think that, see, firstly, the code, these formulas that come now, these formulas are mostly, you will see a lot of empirical things. Empirical means that there are no direct explanation. You won't find any direct explanation of these factors, but they have
Like
done research, and then they give
huh.
some criteria. But I think that this factor should account for what you are saying. But this is practically, it almost never happens. And how, what
And so
values?
I feel maybe, and also ma'am, there is no something called bearing strength of plate. Particularly, we have like how we are having for bolt. There is no calculation for bearing strength of plate. I mean, next in the topics might come, but particularly if you see in the list of these things, when we are
Okay.
considering the strength of a joint, we are considering the strength of bolts like bearing, shear, and tension, and
Yes,
then we
yes.
are going for the tension of the plate. We never particularly see there is something bearing failure of plate. I feel maybe instead of having bearing strength of bolt, we can
Yes.
just have bearing strength of the joint, so that
Yes,
either
yes.
bolt or plate might
Which-
depends
Whichever
upon
fails
their strength.
first, like
Yes.
whichever has the
Huh.
lesser strength, it should be the bearing capacity of the joint as a whole.
Yes. Yes. Huh.
Is that that is how the calculations are done, right? In question, see, in a question you might be asked to find out the capacity of the bolt, but if they ask you to find the capacity of the joint, then you also have to check this part.
Then if we take, okay, so if only the bolt and the just bolt is given, only
Yeah.
bolt properties are given, and if we were asked like to calculate the strength of the bolt, I mean
Yes.
bolt value, we usually consider least of three, but if only bolt is given, I think we will not have any information about the plate and we cannot calculate the bearing. Maybe you're right. Like in the way you're taking the joint, then only bearing comes
Yes, I
into
think
picture.
that I think, have you ever come across a question where this strength of the plate is not given at all? The grade of steel of the plate at least has to be mentioned, because like he
Huh. Yes,
here
yes, yes, yes.
like in this formula you have to know this fu, like the
Hmm.
ultimate tensile stress of plate, and for that you have to know the grade of steel of the plate.
Yes.
I think that in all
Uh,
questions that when they asked about even about the bolt value, the strength of the plate has to be given.
hmm, hmm. Yes, sir. Maybe I should also look into that particular example or something. But I feel
Yes.
it would be like more justified for that particular formula. I feel in that way.
I get you what you mean. Okay, where do you know where is that the tensile?
Uh, 1 second, man. Maybe
Shrikar, what you were saying about the tensile, the bearing capacity of the plate? Do you know where that is in the code?
no. I think there is no particularly right. I'm not aware of that one. That is also my concern. Like there is no particularly bearing strength of a plate. If something is in that way, there is only bearing strength of bolt.
Then I think that, see, wait. Then I think that what you are saying is about they are finding the strength of the joint. They are saying
Joint,
it's the
huh?
strength of the bolt, shear capacity of bolt, bearing capacity of bolt, but it is basically about the joint, because whether the plate fails or the bolt fails, the joint fails, and we have to
Huh.
consider that it has failed. That is why they are
Mm-hmm.
incorporating this, and this factor is likely to account for that very unlikely case that the plate is stronger than the bolt.
Hmm. Right. Yes, ma'am. We will continue with the our session.
Okay. Okay, so we were talking about the advantages and disadvantages of welding. Disadvantages: since welding is a hot process involving non-uniform heating and cooling, the structural members will be subjected to distortion, resulting in more unwanted stress. This distortion is due to the we have that alpha, that coefficient of thermal expansion. So that is quite significant in steel, because temperature fluctuations actually lead to some kind of strains developing in the steel material, so that leads to stress. Welded structures are subjected to cracks due to non-provision of expansion and contraction. There is very high labor cost since skilled labor is required. Now that this is something we looked at during we were studying the advantages of bolting. That bolting can be carried out by unskilled or semi-skilled laborers, but here we need skilled labor. Checking and verification of welding work is very difficult. Again, suppose you have an existing structure, and a lot of jobs that civil engineers get is to go and survey an existing structure to see whether it is still safe or not. So if you go to a steel structure, and if it is bolted, you can see the bolts, you can measure the diameter of the bolt physically. But if it is welded, you have no idea what the dimension of a weld is. Basically, there is something called effective size, so this dimension. But just by looking at a welded structure that is very old, you cannot understand the size of the weld. So verification and checking work is difficult, and the structure may be subject to fatigue and susceptible to failure by cracking under repeated cyclic loads. Tearing of base metal plate may occur beneath the weld, known as laminar tearing. That's because while we are welding, we are melting the plate as well. So if it is not done properly, there may be trouble. There might be trouble. Okay, there are two types of welds: the butt weld and the fillet weld. In butt weld, the two plates are held end to end, and the weld is done in between. And in fillet weld, they are placed perpendicularly like this, and the fillet weld is done in the junction of the metals. So these are the parent material. Parent material is that of the plate, and This is the weld, you can understand. Design strength of butt weld. Design strength of butt weld, either in tension or compression, is governed by the smaller of the yield strength of weld or the parent material. So, like we were just talking, it the strength of a connection is the minimum of the connection itself and and the parent metal or whatever we are trying to connect. So, uh, this is TDW is Fy is the smaller of yield strength of the weld and the parent material. Fyw and Fy. LW is the effective length of the weld, that we'll see what it is. TE is the effective throat thickness of the weld. Throat thickness is, there is a formula between the two. Okay, again I'll open the code since we have it here. I think it was in the appendix or something. Anyway, there is a relationship between the size of the weld and the throat of the weld. And this is a partial safety factor for weld. 1.25 for shop welding, 1.5 for site or field welding. Again, look at the difference in safety factors. Why is shop welding? Why is the partial safety factor in shop welding less? Because see, here we are dividing the capacity we expect by the safety factor, by the safety factor to make it safer. So in shop welding, where when it's done in the factory, we can expect that the conditions are more controlled and the efficiency of the weld can will be higher than, will be closer to what we are expecting. So we use a lower safety factor. While in the site or a field, there are a lot more fluctuations, and that is what after all the partial safety factor accounts for. It accounts for that. Suppose the weld is not large enough as we wanted, or suppose the strength of the weld material is not as much as we assumed. So we'll divide the expected capacity by a certain number to reduce the cell design strength. So in site or field welding, where there are more number of uncertainties, we use a larger safety factor. The design strength of fillet weld in shear is also governed by yield, and it is given by this VDW. I think this should be butt weld. This is the design strength. This is the design strength of weld in compression, tension or compression. This is in shear. T stands for tension and V stands for shear. It is F VW1, smaller of shear yield strength of weld, and the parent material is divided by root 3. All these numbers seem quite random. They all account for some properties or some kind of, basically there is a lot of research work that goes on behind the codes. That there is research, then they come up with parameters, and then they put it in a very simplified or safe manner, in the form of step by step design, so that anyone can do it. All the civil engineers who are designing don't need to have the background knowledge. LW and TE are the same things, and again the partial safety factors remain the same for shop welding or site welding. I think that if it is not mentioned whether it is shop or field welding, we assume it's shop welding. We generally put 1.25. This is design of butt welds. Step 1. For the case of complete penetration of butt weld, there is no need to have design calculations, as the strength of the weld at the joint is equal to the strength of the member connected. For the case of partial penetration of butt weld, the effective throat thickness is computed, and required effective length is determined in order to have strength of the weld equal to the strength of the member connected, and the design strength of the butt weld is computed like this formula. We'll look at an example first. This is a butt weld. Two plates of thickness 16 mm and 14 mm are required to be joined. This is a 16 mm plate, this is a 14 mm plate, and this is the butt weld. They are placed end to end, and this is the weld. The plates are subjected to a factored tensile force of 400 kilonewton. The effective weld length is limited to 180 millimeter. Check whether the joint is safe in the following cases. Single V butt weld is provided, double V butt weld is provided. See, in this double V, it means you are welding from the top and from the bottom. So complete penetration, that means that the metal completely passes through passes through the entire gap between the two plates. So this is the complete penetration case. This is partial one. In case of single V weld, complete penetration of weld cannot be ensured. So the effective throat thickness, this is the formula that you have to remember, that this TE is 5 by 8 of thickness of the thinner member in case of partial penetration. So 5 by 8 into 14. And for shop weld, have they mentioned here? No, so we are taking shop weld by default if it's not mentioned. If it's mentioned field weld, then we'll take 1.5. This is the partial safety factor, and the effective length is mentioned here to be 180 millimeter. So the strength of the weld, again look at this. The Fy is 250 Newton per millimeter square. So that is what we have to use here in Fy. In the formula, 180 into 8.75 into 250 by the safety factor, that is 315 kilonewton. That is less than 400. What do we have to check? If we have to check whether the joint is safe or not, we have to see whether the force, whether the strength of the weld is greater than the force, the factored force. But here the force expected to come is 400 kilonewton, but we are only able to generate 315 kilonewton. So this is not adequate. We have to make a we have to do increase something. Either we have to ensure complete penetration, or we have to increase the effective weld length. And for butt weld, the penetration is complete. So for this case, effective throat thickness is the thickness of the thinner member. See, for partial penetration we multiply it by a factor of 5 by 8, and for full penetration we take the thickness of the thinner plate. Don't make it the thicker plate, because the thinner plate, it's we limit it to there, because this part is not actually welding. This extra part, the weld is between the part between the thin. If you put a thin and a thick plate at end to end, you can only weld up to the thinner part, because the bottom part is not actually connecting the two plates together. So here the LW remains the same. TE is 14 mm, and this 504 is greater than 400. That is the design strength of the weld is greater than the factor tensile force. So this is safe. This is how we design butt weld. Now the design strength of fillet weld. The design strength of fillet weld is given by the nominal FWN is the nominal strength of fillet weld, FU by root 3. The design strength of a fillet weld is a function of throat area and is given by, this is the formula. LW is the effective length of the fillet weld that will be given to you. Throat TT is the throat thickness of the fillet weld. S is the size. FU is the lesser of ultimate strength of weld or the parent material. Again, it generally is the parent material that is the weaker one. PDW is the design strength of weld, and this is the partial safety factor, that is 1.25 for shop welding and 1.5 for site welding. A fillet weld, design of fillet weld is governed by shear stresses, since a fillet weld always fails in shear. See, in this fillet weld, this cannot actually undergo tension at any point. See, in this butt weld, if these two, it is joining the two plates end to end. So if there is a tensile force in the two plates, then the weld metal also undergoes a tensile force. But the fillet weld cannot possibly go, because it's in the junction of two perpendicular bodies, so it cannot actually undergo tension. It has to fail in shear. So the strength that we are calculating is the shear. Yes.
Yes, I'm like sorry to interrupt.
No, it's fine.
Yes, here you're talking about again the butt weld seems to be like only governing in the tensile forces or in tension, and fillet it seems to be like only failing in shear. But
I think butt weld should have it can have shear failure as well, right?
also
Because
yes,
if there is in butt weld, both shear and tension can develop. So
and
there is
that
a
is the
shear
case now.
failure.
We don't have something shear formula for a butt welding condition.
We
Actually,
have
the
this.
PPT is that is right. PPT is right. Actually, the bottom shear what you're talking that is like for fillet only. Actually, that might not be a wrong thing, I guess.
Okay, you're saying that this is the fillet weld. It's not the butt weld at all.
Yes, even for in the sales lecture or something, I was little surprised. I mean, I was little surprised. Like there is no something comparison of shear or yielding in butt, and the same thing with the fillet. There is only one criteria, and that is the design strength. For shear fillet, है तो definitely like in shear, and butt है
Okay.
तो definitely in yielding.
Okay, 1 second. As far as I knew, the butt weld should also have a shear criteria. 1 second.
Hmm.
Have you checked in the code?
No, ma'am.
Okay, I'll see.
And also, I guess your current PPT slide also mentioned like she but fails in yielding only. I guess in the last what you were
See,
showing, not this
this
after
the
the.
yield.
Hmm.
See, the word yield is. It doesn't matter. Okay, yield does not depend on whether it's tension or shear. Yielding is when the that yield stress Fy is exceeded. Fy,
Yes.
every steel material has an yield stress Fy. When that is exceeded, it doesn't matter whether the stress is generated by tension or shear or bearing or anything.
Ha, ha.
Remember when we
It
used to.
will.
Yes,
Yeah,
say.
continue. I'm sorry.
Okay, when we used to study concrete, we used to find out that there were four kinds of forces that we had: bending moment, torsional moment, axial force, and shear force. And corresponding to all the four, we corresponding to torsional moment, we would get a moment, something in kilonewton meter. In bending moment also, we'll get something in kilonewton meter. And for axial and shear, we will get a force in kilonewton. But there were formula to connect that to the stress. Remember that my by I formula to get that bending stress. We
Yes.
similarly had vq by ib to get the shear stress. So all four, whatever be the source of the stress, ultimately it is the stress that is developed in the material, and if that exceeds the yield stress, the material fails. Yield is not related to tension or shear. Yield can be due to anything. Okay.
Okay. Hmm.
Tensile yield, shear yield. Okay, so now what were you saying in the about
Uh,
the PPT?
I mean about the PPT. If you go to slide number 23, I guess after that sentence saying
23 was the example.
no, sorry, after the example, I guess. Yes, sorry, 22 only, ma'am. Itself. The bold letters, the then of fillet weld is governed by shear stress
Shear.
only. Yes.
Yes, that is fine. Fillet weld is governed by shear, but is butt weld only governed by tension? That because I think that butt weld can also fail in shear. Butt weld can fail in both. That's what I'm saying. Just 1 minute.
Also, in the problem when we're doing the regarding the butt weld, we didn't compare anything
Did
with the.
yes, exactly,
Hmm,
exactly. That's what. 1 second.
yeah.
Yes, and we actually should have if that was a possibility, because here we are dividing the strength by root 3, so this should be the critical case.
Uh, Also, one more thing, like,
Yes.
will there any situation where the strength of the welding material, like what we are liquefying and keeping there, is there any situation where we use lesser strength compared to the main members?
I don't think so. I don't think that is at all possible. Even bolts, I have never heard of the bolt strength being lesser than the
Lesser,
material, than the parent material. Because see, the connection is actually, they always say that connection is the most critical part of a steel design, the design of a steel structure. So the connection they always try to make stronger than the parent material.
so I am guessing in that way, maybe in butt weld, there is no
Yes.
possibility where shear fails comes in the welding,
Okay, okay.
and
Because you'll say
only
the metal will fail before that. The plate will fail
ha
before that it even reaches the weld.
reaches the weld.
So we are designing before that. Right. I think that's the explanation here.
And
But
also,
see,
ma'am, while we
yes,
are considering for butt weld, the we are considering the yield strength. But see, even though that's what you're talking about butt weld, still
this
goes
one.
on some kind of in general butt weld. Yes, we're talking about butt weld. The value TDV is equal to
Yes,
Fy by and why we are considering that is the criteria like Fy value. Still,
yes.
it was not like failed. It was just it will be like yielded, and we have still some kind of strength. Which it can still withhold
Exactly,
the
exactly.
connection.
You are saying why are we not using the ultimate stress?
Huh,
Why we are
huh.
using the yield strength? See, this is one philosophy. Again, why are we using the partial safety factor as well? Because once the material has yielded in this you can see that once this is the yield point, this CD thing, after once
Hmm.
the material has yielded, it starts flowing. So if the weld has yielded and it starts flowing, there will be a lot of displacement between the two members that it is connecting. So
Okay. Hmm.
eventually the connection has failed, and the connection will there can be movement developed between the two sections, and there will be, there will be a redistribution of force, and ultimately it can
Structure.
stress, the
Complete
stress
structure
will,
will be.
yes, the structure will be affected. But again, the entire thing is a trade off, because between safety and economy, right? So a lot of things that we do, that like put these safety factors and we allow it only up to the yield strength and not the ultimate strength, it is that we don't want to push the structure so too far, we want to keep it on the safer side. You will never see the opposite, you will never see we are making it on the unsafe side. We always allow lesser strength to be generated than it actually has, so that even in the case of an unexpected loading or something, if suddenly a very large earthquake comes, or a very or extreme wind comes, or it is overstressed, so that even then it only goes up to the yield strength, or a little less, or a little more, not completely. We don't want it to collapse all at once. So these are all safe.
But to be frank, ma'am, that is why we came to the design philosophy of limit state. See,
Limit
working
state
state
design.
method is it was using the FY, so that's why there is still strength. That's why you came to the limit state. We don't doesn't making
In
any economical thing, and that is the reason, I guess, the main reason. I mean, major difference between the working state and limit
Because
state, I
we,
guess.
yes, in the working stress we only
Huh.
allow up to yield, but in limit state we want it to go up to the ultimate strength. That's what you're
But
saying,
maybe
right?
that point, yes, and also maybe the point where you mentioned previously, like even the smallest yield in the butt weld, maybe the total structure will be having much
In
worse.
weld, I think that if yielding starts, then especially in connections I don't think fu is ever used. Is it used?
Again in fillet weld,
Fillet
they are
weld,
using.
okay, they're
Uh,
using fu in fillet weld, but not in butt weld. I think it has to do with the positioning of the butt weld, because if there is
Maybe.
any kind of yielding, the members will completely come apart immediately, because the strain
Hmm.
starts increasing. But the fillet weld is positioned in a different way. Even in case of yielding, the members are placed in such a way that it can take some kind of strain. It is also a good question. Wait, I'll write these down.
Yeah.
Your first question was about the high tension grip bolts, right?
Yes, ma'am.
One second. I'll look into these two and let you know next class.
Sure, ma'am.
Okay, and also about why we are not. I'll just confirm why we are not checking the shear criteria and butt weld. Okay, so for fillet weld, we only check the shear criteria. So we look at an example here. Yes, a channel section is required to be welded to a 10 thick gusset plate. Okay, what is this? Gusset plate is a concept that you probably haven't come across so far. Gusset plate is used to connect two members. I'll show a photo here. It'll help you to visualize. See, when there are several members meeting at a joint, we cannot just bolt them on one on top of the other if the arrangement is to be like this. So this blue thing is a gusset plate, so that it is just an intermediate where all the members come and meet, and we can bolt or weld it to the gusset place instead of to each other, because otherwise, if there are 5 or 6 members meeting at a single point, you can't keep on placing them overlapping, so the bolts won't be long enough, and it won't work out and the welds will also not work out like that way. So the gusset plate helps when multiple sections come at a point. So there is a gusset plate and the channel section is to be welded. This is the gusset plate, this is the channel section. Can you see how this channel section is like? Basically channel is a C section, these two are the where the flanges, and this is the web. So it is placed like this. So the C is facing towards you, or away towards us, and the web or the body is placed on the gusset plate. The channel is required to carry a factor tensile load of 750 kilonewton. The overlap of the channel section on gusset plate is limited to 280 mm. So, and this channel is mentioned to be ISMC 250. Again, this code, I think if I could show you one of these, it would help. It is in C61. See, this is a section handbook. See, they said ISMC 250. So this is ISMC 250. This is the properties on this line. So I'll see the headings: weight per meter, sectional area, depth of section, width of flange. All these, see, this depth of section H is marked. This is the shape of the channel. This H, this depth is marked here. ISMD 250, it is 250. So these numbers are basically the depth of the section. This is the width of flange, the thickness of flange. All these numbers will be mentioned. So in the question, only this will be mentioned, and you will be given these data, or you will be allowed to carry a code. So since this is ISMC 250, and we saw that the thickness, this is that thickness part. So we know that this will be 250 mm. Don't just assume because this is 250. We are not sure that for all kinds of section 250 will be this depth, though it generally is. This is 250. This overlap is 280, so this will be 280, 280. So if you want to weld, which part you are going to weld is that if you are welding this channel on top of this gusset plate, you will weld along this and this. Anyway, let's see the question. Welding is to be done at site, so we have to take the safety factor as 1.5. Using Fe 410 steel, design the weld. The channel section used is ISMC 250. For grade of steel 410, Fu is 410 and Fy is 250. Partial safety factor is 1.5 for ISMC 250. See, these are all these values that they have written here is exactly comes from here. This this 3816 is the, this is, I think it might have been updated sometime, but yes. So anyway, these are the properties 80 14.1. These are what they have they have listed out here. You don't have to remember these, obviously they will be provided. And we are designing, since we are designing something, from design of concrete structures, that we have to assume something. We have to assume a dimension first. We will assume a dimension, then we'll check if it is enough. If it is enough, it's fine. Otherwise we increase the dimension and check again. So it is a iterative process. So let us provide the size of weld to 5 mm, and the effective throat thickness. Again, this is the formula that we use for fillet weld. zero point 0.5 in 0.7 into 5. The design strength of weld is given by this. Okay, the this length available for weld is, they have done it like they have first found out the strength of the weld per length and then multiplied by the length. But we can do it. We can multiply the length initially. That 280 plus 280 plus 250 mm. That is, this 810 mm is the length of weld. So we can put the LW as this. TT is 3.5, FU is 410. That is the ultimate strength that we use in fillet weld. I will let you know next class why we are using ultimate strength in fillet weld and yield strength in butt weld. Divided by root 3 into 1.5. So here they have basically, they have, what they have done is they have found out the strength of weld per millimeter length. So they have put 1 in place of LW. that is 552. And for a factor tensile load of 750 kilonewton, they have found out the length of weld required first. They have done it in an inverse manner. So 750 into 1000, you have to just be careful about the units. Here it's kilonewton, and here we are getting newton per millimeter. So you know that newton per millimeter is megapascal, right? Because we are putting 410 megapascal in fu. So whatever value of whatever unit of fu we are putting, we are getting the strength in that unit. So it's this is megapascal or newton per millimeter. And that's for factor tensile load of 750 kilonewton. 750 into 1000 divided by this is 1357 mm. So to generate a strength equal to or greater than the factor tensile load, we need at least 1357 mm of weld length, but the overlap limit is 280 plus 280 plus 250, that is 810. So we cannot provide the amount of the length of weld required, so we have to redesign it. So so there is one thing that can be done is slot welding. Okay, slot weld is basically, if the overlap is uh, limited, then one thing you can do is you can increase the effective size of the weld. You can try this with 7 mm or 8 mm, and you will probably find it's fine. Another way is keep the size of the weld what we have assumed, but increase the length of the welding. So if you can cut the section like this, you will see that the weld will go like this. So the overall the effective length of weld is increasing. So the shortage of weld length is around 550 mm. So the slot welding has to be provided. This this is basically an algebraic calculation. This length is 4L. This 1 2 3 4, this is the slot length. Okay, so there are 4L plus, there is 2 plus 2 into 250 plus 250. I think they don't count this 25 mm part. They only can count the these length parts. Oh no, they are actually, it's fine. It's this. If you visualize the entire length, you will see that one 280 is coming, another 280 will come, and then four of these L will come, and this width will remain 250 overall, because this plus this plus this plus this plus this will be 250. So this L they find is 80. So you have to round it off, and because since you are designing, you can, if you get that the required length here is 80.39, you can't do it 80, you cannot reduce it, you have to always provide a safer one. So since by increasing effective length the strength increases, you have to round it off on the upper side. So you could have done it 81, or they have done it 85 to get a round figure. So you have to provide a slot length of 85. Otherwise, what you could have done is increase this this 5 mm to 7 mm and 8 mm, and then redo this calculation. And if that was enough, then you did not have to do slot welding. Okay, I think this should be enough. This is a very specified problem, the last one. Are there any questions?
Regarding the lecture, there is no question. Like I do have one more question regarding a problem in bolting connection. Can
Okay.
I ask now? Is it the time? Is it fine?
No, you can ask me now.
Okay, but ma'am, do you have access to Sir's PPT?
Yes, Damodar sir's PPTs.
Yes.
Which question? Which lecture? Or you can, are you allowed to share your
One
screen?
second. Uh, I'm not sure. Maybe I can.
But if I stop presenting.
Oh, one second, ma'am. Even I will open up the sheet. I do have,
Okay,
but
okay.
not in the slide. I will just open the slide and I will share. Okay, I was not able to find the problem, but I remember it.
Yes, you can take your time. There is
Yes.
time. The others
Okay.
can leave
Okay.
if they want.
Huh. Were you able to see the question?
Just press don't show this again on the infinity mirror.
Okay.
Yes.
Now are you able to?
1 second.
Yeah.
It hasn't appeared yet. No, it's showing a black screen. Can you see
Okay.
it?
1 second. Maybe I'll change the option.
Okay.
Oh, now, ma'am.
Yes, yes, I can see now.
Okay. In this particular question, this is regarding 1 second. This particular question.
Yes.
Okay.
Two plates 10 mm thick are joined by 16 mm diameter bolts in a triple staggered lap joint. Find the efficiency of the joint.
So
Okay.
can I go to directly to the question, or will you just read the steps and all?
No, first go to the question. I mean, what your doubt is?
Okay. Okay. Right. So yes, if you see the strength of joint along 2 2,
Yes.
here they're mentioning about this particular section,
Okay.
and we are seeing this is a case where along the joint strength of the joint along 2 2. So they are calculating the strength of the plate as well of the bolt values, like these particular bolt values. I mean, they I guess they're saying that if the section it was failing about the section 2 2,
Yeah.
then it has to fail with respect to the bolts before them, like with together. I
Okay.
feel it doesn't matter even these bolts need to be failed. There can be a possibility case where only along the 2 2 can be failed, but there is no that kind of consideration. There is like have to consider this one. Same with the 3 3. If the bolt is failing around 3 3,
Okay. So three they are saying that first the line one has to fail,
huh,
then line two has to fail,
line 2
and
has
then
to
line
fail.
three has to fail.
Huh. And also, ma'am, we have an assumption saying that all the bolts, I mean, we assumption is like all the bolts will have equal amount of either shear or tension, anything, whatever the force is coming. If on particular only on the bolts, then in that case, if there cannot be a situation where this bolt fails and this bolt cannot.
Yes, I mean that shouldn't happen. Why are they taking from left to right?
I do not
Okay.
know. Even they didn't mention any force like action of force where it is there. But see, even though it was represented towards right only,
Hmm. So anyway, no, there cannot be a force towards right only. Tension is always
hmm,
a coupled force.
coupled force, yes.
There will be pulling apart on both sides, on both ends. So tension is not that sort of force which goes in
Yes,
one direction. It's
one
a coupled
direction,
force.
yes.
So
So
okay,
yes, ma'am, this is my question. Yeah.
They are saying, see, the 3-3 part is not very concerning because of with respect to 1-1 and 3-3, it's a symmetric structure. So
Huh.
the 3-3 is if they add this 5b value, it is always going to be higher and it is never going to fail that way. It's the 2-2 that is a concern, that they are adding the two bolts. So
Huh.
wait, if the two bolts, you're saying that even if the that two bolts in a line one doesn't fail, the three bolts there can fail.
I mean, here we are talking about. I think this is joint. We're talking where the plate fails actually. Huh. Actually, I think we have gone to the bolt failure. Here we consider the bolt value failure,
Yes.
and we are talking about only the joint. Okay, only the joint failure. Yes, yeah, right, ma'am. I think. Again, if we consider joint failure, there should be like failure of these three bolts along with this section. But we are considering these two bolts and this
These
section.
two, this section. See, if those two, right? 1 second.
Hmm.
Is there any stipulation like this in the code? Wait, in this case of staggered bolting,
Hmm.
I think there was in Sir's lecture. Did he mention any of these?
He just went through the steps and he just completed. He didn't particularly say like he did mention like he was saying like if there is a failure at the section 2 then the bolts 1 1 have to fail. He mentioned in that with that, but he particularly didn't explain what exactly happened. Like a statement he has given like 2 it was, if it is going to fail, one these two bolts has to be failed.
Yes, intuitively, that is what is actually going to happen. That you can. No, but
But
I
but
also
but
will
the
tell you
basic
that.
assumption, we have like same number of like same kind of forces coming onto all the bolts. That will be like contradictory, right?
If the same force is coming on the board, then what did you say?
I mean, we have the assumption like or in a bolted connection, the same force will come on the same kind of forces.
Yes, yes, you have that
Huh.
connection. They are not assuming that it is coming one by one from the outer one to the inner
Yes.
one. There is no such
At a
assumption.
time, yes, ma'am. At a time, in almost like equal forces will be coming.
Right, right. Staggered left and 1 second. I think either I understand what you mean. I mean, I can imagine only the central part tearing off and the other parts remaining intact, right? You are saying
Huh.
that only the two it fails in the two part only. So
Yes.
I think there has to be some kind of stipulation in the code that makes us calculate this way.
Okay.
But okay, I'll send you the link of this first. I'll send you the link of the IS 800 in this chat box. Okay, because since
Okay.
you are studying the subject with so much interest, going through the code will really help you. And I also have to look through this the exact part that you are saying. I'll add that question as well.
Even I was not able to imagine like how would that happen, like the failing of the bolts in the along 1 1 section and the plate failing in the 2 2 section. I was not able to imagine like
No,
so that I
no.
was not.
Basically, no. What they are saying, what this calculation implies is that two that once the once the developed stress has overcome the strength of the two bolts, the entire force it has to be taken by these three. Okay, because otherwise the force is taken up by the entire joint together. So once the force has what happens is that when there is an assembly of structural elements collectively taking a force. One part
Mhm.
fails, one member fails, and then there is a force distribution, and then the other parts have to take the entire force. So
Mhm.
what this says is that the first line of defense, you can call it, that has
Mhm.
given way, so the entire force has been transferred to that line. But again, you are saying that they have mentioned that there is equal distribution in all the bolts, so then this argument does not hold anymore.
Huh. I mean that sentence is not given in that particular question. It was like mentioned in the starting of the lecture, like kind of exemptions for
Okay, okay.
were
I think what they are saying is that once that till the two goals in the line 1 1 and 3 3 holds, the force does not come in the line 2 2 at all. And then once one has failed, it comes to the other one. But even I have a little trouble imagining that. I will get back to this next class.
yeah, sure, ma'am.
Which lecture is this?
This is lecture 2, ma'am. Lecture 2, it was like in the 24th slide, I guess. Yes, 27th slide. Yeah, 27th slide. Lecture 2.
Lecture
Yeah,
2.
lecture 2.
Okay, okay. Can you show me the picture once? I'll take a
Yeah,
picture
sure,
of
ma'am. One
the
second.
question. Okay. And I sent a link of the PDF of IS 800.
Yeah.
And I'll also. Do you have the sectional steel book that, like, SP6? Yes. I think both of these you should have, the IS 800 and SP6, which gives the section details. Okay, then.
Yes.
We'll meet again next class.
So, did you have your session in last week?
Yes, I had it. Why? I mean, this.
Actually, I was not. Actually, this is the first session I was attending to your particular session, but I was watching all your sessions. But I think you did not upload the fourth session. Can you please upload the fourth session
No,
also?
this is the fourth one. My third one was the bolted connection. This is the fourth one.
Okay. Okay. Oh, okay then. Right.
I think I am going a little different from the exact lecture division. I
Might
think
be.
there were two on bolted connection or something.
Okay. I'm not sure because the since the actual lecture is going on in the NPTEL like in fifth week, I was guessing this is the fifth session. That's why I was little in
Okay,
that
okay. So
way.
now currently now welding hasn't started in sir's classes.
Yeah, it is started, yes. Actually, we crossed welding and we went little tension of the
Tensile
plate is
tensile capacity, that part. Okay, okay. Next class I think is about tensile capacity of plates. One
sure.
second. I'll just. Yeah, the next class is eccentric connections.
Oh yeah. Yes.
Okay then. Uh,
And I have to sorry, ma'am. Like one more thing,
yes,
and
yes,
I'm
yes.
very thankful. You're talking to like complete explanation is given from your side. I liked so much about your your sessions.
Okay, thank you, thank you. I'm glad someone is benefiting from this.
Because not only just following the yeah, you're also talking about the behavioral and the strength of materials kind of thing. You're considering that part also. That
Yeah, I know, I know. I know that really helped me when my father taught me. So my father is a civil engineer, so he starts with these things more than the actual calculation parts, and it's important to visualize it. Otherwise, there's no interest in the subject.
yes.
Okay,
Right, ma'am. Thank you so much.
okay. Meet you. See you next class. I'm ending the session now. Then. Okay.